You're all welcome to this session of vector calculus, and this session is a continuation of line integrals we did in the previous video, where we looked at line integrals of vector fields. Today we are going to concentrate on line integrals of conservative vector fields. So if you have a conservative vector field, let's say f in 2 dimension, which is x in the I direction plus y in the j direction, or we have it in space where our conservative vector field f is equal to xi plus yj plus zk. Or it could be functions in x, y, z, or f can be a function in, let's say, p of x I plus q of y j. Or we can have also a function in x, y, and z. So we can also have in 3 dimensions equal to p of x, y, z, I in the I direction plus q of x, y, z in the j direction plus r of x, y, z in the k direction. So we can also expand this one where we have x and y. This one is also x and y. And so we learned that the formula for finding the line integral is line integral about c, the path of integration is given as f of r of t dot r prime of t dt, where this integral actually measures the work which is done by this force F on an object, and that one from along this path which is given as a path of this is C. And so we can quickly take an example where we are dealing with conservative vector fields. And so let's take an example. If f, which is a conservative vector field of x and y, is equal to 2xi plus 3yj, find the line integral from a path C1, which is made up of moving from a point 0, 0, 0 to the point A, which is x is 2 and y is 0. Then we can also find the line integral along another path C1, C2, where we move from the point to, let's say, A 2, 0 to the point B, and point B is given as 2 and 5. Then we can also find a line integral along another path, let's say path C3. In this case, C3 moves from 0, the origin 0, 0, 0 to the point B, which is 2 and 5. So it means that we can find line integral along designated path. And so we'll look at a situation where we'll find the line integral of an object through different paths. So we have path 1, path 2, and then path 3. And then maybe eventually we will analyze the situation where we go around the path. That is point D around the closed path. That is, we could start from the point 0, move to point A, then point A will move to point B, and then point B will move back to point A, point A. And so that concludes the line integration around a closed path. And so we can quickly take this one off and then work with the first path, path A. So we can quickly take this one off, and then we'll look at path example A. So our example A. So looking at example A, we'll look at the solution. So it is always better when we are given the path of integration, we represent it on a graph so that we can know how the particle moves. So let's draw the Cartesian plane where we have the x-axis and the y-axis and 0. And so the path C1 is from 0, 0, this point 0, 0 to the point A. Point A has coordinates 2 and 0. And then that is, this path is C1. So we are going to find a line integral along the path C1. And then B tells us that we should find a line integral from point A to point B. Point A is 2 and 0, and point B is 2 and 5. So if this is 5, then this is point B, which is 2 and 5. So it means that we are going to find the line integral along the path AB, and that will be C2. And then we are going to look at the third one, where we move past path 3, C3. We can move from 0, 0 to B, which is 2, 5. I can also move from 0 to B. So we can have the line integral that's around the path 3. So the fourth one, the D1, it means that we want to find the line integral along the closed path, as is on C1, C2, and then C3, along negative C3. That concludes the integration along the closed path. And so let's take example A. Example A, we know our conservative vector field fxy is given as 2xi plus 3yj, which we can put it conveniently in the bracket as 2 and 3. 2 and 3, as 2 and 3. Now, path C1, along C1, we move from 0, which is 0, 0, to point A. A has coordinates 2 and 0. And so we need to find the the path on which the line integral is being calculated. So R in this case is given as R of t, which means that we have to find the parametric equation of R, which represents the path C1, that is from 0 to the point A. This is A, right? And so it's given as 1 minus t into 0, 0, the first point, initial point, plus t times the final destination, 2 and 0. In this case, the parameter t is always defined, in this case, as a line between 0 and 1. And so let's continue along the path C1. And so when we multiply, we're going to have 1 minus t times 0, that will give us 0. 1 minus t times 0, that will give us 0, plus 2 times t, that will give us 2t. T times 0, that will give us 0. And so if you add the coordinates, that is the I direction and the j direction, you're going to have 0 plus 2t, that will give us 2t. And then 0 plus 0 will give us 0. And so that is the parametric equation of the path which is given as this. And so let's check if the parametric equation of the path C1 is correct. The points C1 starts from 0, 0, where the parameter is 0. So if you put 0 in place of t, realize that we will get 2 times 0, which is 0, 0. And so that shows the coordinate of point 0, O. Now let's come to the final destination, where A is equal to 2 and 0. In the final destination, t corresponds to 1. So if we put 1 here, we're going to have 2 times 1, which is 2. 2 and 0. And that corresponds to the final position A. And so once we are able to find R of t, we can also find R prime of t. We can differentiate the path. We can differentiate it. So if we differentiate it, we're going to differentiate term by term. If you differentiate 2t with respect to t, you get 2. And then if you differentiate 0, you still get 0, right? And so now f in terms of x and y is giving us 2x, giving us 2x then 3y. So that is 2x and 3y. So we have to find the parameter. We have to parameterize this f, and so we know x. We know x is given RTX, and so we can parameterize it and get f at R of t. So it means that instead of using x and y, we're going to substitute the values of the corresponding values for x and y in the parametric equation of the path. And so in this case, the path for the x is 2t and the y is 0. So substitute 2t here. So 2 times x is 2t, and then the y2 will be 3 times y. In this case, y is equal to 0. And so when we tidy up, we're going to have 2 times 2, 4t, and then 0. And so that gives us the vector field along the parameter r. And so with that one, we can slot this one into the equation, that is finding the line integral. So we're going to have the line integral of C1, that is f at r of t dot r prime of t dt. And so we put in the values there. F of r of t is what we've gotten here, and that is so f of is r of t. So r of t now becomes 4 and 0. So 4t and 0. So 4t and 0. Dot r prime of t. R prime of t gives us 2 and 0 times dt. So we're going to find the dot product, and then our t is between 0 and 1. So the lower limit will be 0, upper limit will be 1. And so before we integrate, we're going to find the dot product of the integrand. And so that gives us integral from 0 to 1. That is 4t dot 2, which is 4t times 2, that will give us 8t. And then if you dot the y coordinates, 0 times 0 will give us 0. So times the t. So now we have reduced it to this integral. And now we can integrate this one. If you integrate 8t squared dt, we are going to get 8. If you integrate 8t dt, we're going to get 8t squared, 8t squared over 2. And the limit is from 0 to 1. And we know 8 divided by 2 will give us 4. So 4. So we're going to have 4t squared, 0 and 1. And if you put the upper limit 1 squared will give us 1. 1 times 4 is 4. Minus the lower limit. The lower limit is 0. So if you put 0, then it becomes 0. So there's no need to put 0. So it means that along the path C1, the line integral along C1, the line integral of f of r of t dot r prime of t dt should give us 4. We are going to look at C2, the path along C2. And so we can quickly take this one off, and then we will find the line integral along the path C2. So along C2, from C2, which means that we moved from A, which is 2 and 0, to B, which is 2 and 5. And so we need to find the path, find the parametric equation of the path r of t is giving us the formula 1 minus t initial position, which is 2 and 5, plus t times the final position, which is 2 and 5. It's 2 and 0 and 2 and 5. And of course, our parameter in this case lies between 0 and 1. And so if you open the bracket, you will see that 1 minus t times 2 will give us 2 minus 2t straight away. 2 times 1 minus t give us 2 minus 2t. And then in the y direction, 1 minus t times 0 will give us 0. Plus t times 2 will give us 2t. Then t times 5 will give us 5t. And so when we add the corresponding coordinates, the I components and the j components, we're going to have 2 minus t plus 2t. And then we're going to have 0 plus 5t. So that will give us, if you tidy up, we're going to get minus 2t plus 2t will give us 0. So here we'll give it 2, and 0 plus 5t will give us 5t. So once we've been able to find r of t, we can find r prime of t. Which means that we are going to differentiate it. So we are differentiating this term with respect to t. So if we differentiate 2, which is a constant, we get 0. And then if we differentiate 5t with respect to t, we get 5. And then we have to parameterize the vector field. And so f of r of t will give us, instead of x, we have 2x. X is given as 2. So it means 2 times 2. Then the y component will be 3 times y. 3 times y, which is 3 times y. And y is 5t. So 2 times 2 will give us 4. And then 3 times 5 will give us 15t. And so we put this one into the line integral formula. which is line integral about the point C2, around the path C2 of f of r t dot r prime of t dt will give us the integral f of r of t give us 4 and 15t dot r prime of t give us 0 and 5 times dt, and the integral t is between 0 and 1. And so when we do the dot product, it is 0 and 1. We're going to have 4 times 0 will give us 0. We don't write it because it's 0. That's the I components. And then the j components, 15t times 5, which is 15t times 5 dt. So that one will give us integral from 0 to 1. And then 15, this will give us 75t dt. And if you integrate 75t dt, you're going to have 75t squared over 2. And the limit is from 0 and 1. So the upper limit will give us 1. 1 squared will give us 1. So we're going to have 75 over 2. Definitely the lower limit is 0. So if you put 0 here, the lower limit becomes 0. So we have for the path C, the path C2 will give us 75 over 2. So the line integral along C2 of this line integral C2 f of r of t dot r prime of t dt. Then the line integral along C2 will give us 75 over 2. So we're going to look at the third scenario where we find the line integral from O to B. So we are going to find the line integral along the third path, which is from 0 to B. So we can take this one completely off so that we find the line integral. And that one will be from that is C3 along C3, and the point is point 0, which is 0, 0 to point B, which is 2 and 5. And so R of t will give us 1 minus t initial position, which is 0, 0, plus t 2 and 5 and 5. And so when you multiply, you're going to have 0, 0 plus 2t 5t, and that will give us 2t 5t. That is r of t. Now once you have r of t, you can find r prime of t. That is differentiate respect to t. So if you differentiate respect to t, you're going to have 2 here. If you differentiate 2t respect to t, we get 2. Differentiate 5t respect to t, we get 5. And so we need to also parameterize the vector field. So f of r of t will give us r of x and y is 2x 3y. So instead of x, the x is giving us this one 2t, and then 3 times the y. The y is equal to 5t, and so this one gives us 6t and then 15t. And you get 6t and 15t. That will be the vector field. And now to find the line integral along the path C3. So that is C3, and that one is F R of t dot R prime of t dt now becomes 6t 15t dot R prime of t, which is 2 and 5 dt. And obviously our t is always between 0 and 1. 0 and 1. Let's check. If at the initial point, when t is 0, when t is 0, you put it here, you have 0, 0. And at a point B, where the coordinate is 2 and 5, which corresponds to 1. If you put 1 here, we get 2 and 5. So we are on the right path. And so we are going to find the dot product. That will be integral 0 to 1. That is 60 times 2, 60 times 2 plus 15t times 5 dt. And so when we tidy up, we're going to have 12t plus 75t dt. And so if you add 12 to 75, obviously you're going to get 86 t dt. And if you integrate 86 t dt, so if you integrate 86 t with respect to t, we'll have 86 t squared over 2. The limit is from 0, 1. 86. So 86 divided by 2, we're going to have 43, and then the lower 43 t squared, and then 0, 1. And so if you put the upper limit, which is 1, then t squared, which is 1 squared, is 1. So that will give us 12 times plus 75 will give us 2 plus 5 is 7. So this one becomes 87 rather. So we can't divide by 2, so it becomes 87 divided by 2. And if you put the upper limit, we're going to get 87 over 2. And so if you integrate along the third path, C3 of f of R of t dot R prime of t dt, we're going to have 87 over 2. And so let's analyze the answers that we have gotten. It means that when we decided to move from point 0 to point A, we had 4. And if we moved from point A to point B, we had 75 over 2. So having calculated for line integral along C2, we are going to find the line integral along the path C3. So along C3, C3, we know f of x and y is equal to 2x and then 3y. And then along C3, we are not going to bypass it. We are moving from 0, 0, 0 straight to B to 5. And what did we get? We also had 83 over 2. And so what this one means is that when you have a conservative vector field, then the work done, which is always associated with conservative vector fields, does not depend on the path that you take. Does not depend on the path you take this at all. And so you could even decide to move from point O to point B, not on a straight path, but even on a curve, whatever curve you have. Whatever curve you have, the work done will still be the same. So interestingly, let's look at the last part, the D, where we're going to find the line integral along a closed path. So it means that if we want to find the line integral, that is from C1 to C2, then C3's direction is in this way, but we want to move from 0 to A, C1, then move from A to B, C2, and want to move back from B to 0, which is C3 by the opposite direction. And so that one will give us the negative of C3, the negative of C3. That is C3, we are talking of vector fields. Vector field direction is very important. And so OB gives us this direction in this direction. So if you want B to O is a negation of the path which is C3. So minus C3 of F of R of T dot R prime of T dt will be equal to moving along C1. C1 give us 4. Along C2 give us 75/2. Then along C3, negative C3 give us 83/2. So negation of that give us negative 83/2. And so when you sum it up, we're going to have 83/2 minus 83/2, and that gives us 0. And so one characteristic of the conservative vector field is that if you find a line integral along a closed path, f of r of t dot r prime of t dt around a closed path. In this case, this is a symbol for around the closed path, which means that we started from O to A, and then to B, and then back to O. So it means the integration around a closed path. And so that gives us the value 0. It means that, 1, if F is a conservative vector field, then it doesn't matter the path that you take. When you start from a point, go around in any haphazard way, and you come back to the original point, then the work done along that path is 0. So in situations, we get situations where this line integral along a closed path, let's say f of r of t dot r prime of t dt is not equal to 0. When we do a line integral along a closed path, and the integration gives us a value apart from 0, then it means that that vector field f is not a conservative vector field. But let's take note, if f is a conservative vector field, then the line integral along a closed path becomes 0. It is not 0 because if f is not a conservative vector field but any other vector field, then you will never get the line integral along a closed path, which is 0. And so we also learned that the conservative vector field f, we can always find the conservative vector field from nabla f, where we learned in our previous videos that f is the potential function. F is the potential function. And then small f potential function. F is a conservative vector function or field. And we know this to be del or nabla. And so in this case, we also learned that if f is a conservative vector field, we know that F cross F cross del, or del cross F. After calculating, we saw that the line integral along the path C1, C2, and the opposite of C3, which is minus C3, gave us 0. And it's very interesting. How do we get the value 0? We got the value 0 because if you do the integral of f of r of t dot r prime of t dt, that is around a closed path, it's a closed path, around a closed path, that's a symbol for a closed path, that's a closed path. It means that we started from point 0 to A to B, and B back to 0. Then we saw that the integral gave us 0. Because F in this case is a conservative vector field. So if you have found a line integral along any closed path, and F is a conservative vector field, then your integration obviously will give you an answer of 0. However, if F is not a conservative vector field, then the integral around the closed path, F of r of t dot r prime of t dt will never be equal to 0. In this case, when you do the line integral along a closed path and the answer is 0, it's not 0, then it means that F is a vector field. It's not a conservative vector field. And so we learned from our earlier videos, other lectures, we learned that F conservative vector field is always calculated from nabla F, where F is a potential function. And then our F obviously is a conservative vector field. And also, we learn from our knowledge in cross product that if you have cross product of nabla with the conservative vector field, the answer will always be 0. Provided F is a conservative vector field, the cross product of nabla and the conservative vector field is 0. And we saw this in one of our assignment 3, where we found the cross product of a conservative vector field, and the answer was 0. And so on this note, thank you very much, and I hope to see you in the next videos where we'll treat other topics in vector calculus. Thank you very much, and enjoy your day.